Hello everyone! So today I'm going to be doing another lesson on force and momentum, and today I'm telling you about conservation of momentum, which is actually one of my favorite topics. So let's give it a start. So first of all, I need to tell you about forces, and you will see why in a second. So if you remember from some videos ago, and probably in another playlist, I have a lesson just on Newton's laws of motion. And Newton's third law of motion says that when two objects interact, they exert equal and opposite forces on each other. So it's the law of action-reaction. And I have here some examples. Oh, actually, I also have the Newton's third law of motion, which is not the one that we are going to talk, okay? So I have some examples in there. So look at, for example, the guy and the boat in the water. So imagine that he's going to jump on the water. That's the action. But when he's jumping, his feet are making a force to try to get him to jump. So as he wants to go forward, the feet are going to make a force on the boat. And this is going to make the boat move backwards because he's just trying to get enough impulse to actually jump. So that's the reaction. The force that the guy makes and the force that he is able to jump is going to be the same as the force that the boat feels on the other direction, okay? The same there with those two guys with the skates. They push each other. Imagine that they are stationary. They push each other with the same force. They will both, one pushes the other with a force of 50 newtons, and then as a reaction the other feels the force of 50 newtons, moves backwards, but the guy that made the force also moves backwards because again the forces in one object is going to be the same on the other object, it's just in opposite directions. It's like the rocket as well when it goes to space, you know. The force is the exhaust gases, and then the reaction of that is the rocket going up, okay? Now, you may remember as well that I told you some lessons ago that I can get that to show that force is going to be the derivative of momentum over time. And I have there the explanation. Force equals mass times acceleration, which is Newton's second law. And I can say then, therefore, that's equal to mass times the derivative of the velocity over the derivative of time. Because mass is a constant, can go inside, so I can get the derivative of mv over dt. And mv happens to be momentum, so I get dp over dt. So force is dp over dt. So in interactions, objects can transfer momentum between them, but the total momentum is not going to change, it's conserved, because as you know, the forces are going to be equal and opposite. So then, that means that if this number in total is equal and opposite, so you have a zero, then the other side needs to be constant, okay? So for a system of interacting objects, the total momentum remains constant, provided that no external resultant forces acts on the system, and that's known as the principle of conservation of momentum, okay? I was just saying moment. So there it is, provided that there are no external resultant forces. So that's why you need to be careful when you think about that F in there, okay? So the law of conservation of momentum, I don't know why I'm saying moment today. The law of conservation of momentum says the following. When two objects interact, the total change in momentum of the two objects, taking the direction into account, is zero. The reason why that part saying taking direction into account is zero is very important is because momentum, yeah, I was thinking that I was going to say moment. Momentum is a vector. So that means that in one direction you can consider it to be positive, and in the opposite direction you can consider it to be negative. So if you don't take the direction into account, your answers are going to be wrong, and therefore the law of conservation of momentum would be wrong, okay? So that law basically tells you that the total momentum before the interaction equals the total momentum after the interaction. And I like that people use the formula there on the bottom, this one, as a start of the momentum questions, because it's going to be a good way that if you follow that formula, you're definitely going to get everything right, okay? And then it works as well when you have more than one it's not the word variable that I want to say, but I cannot remember the better word. When you have more than a variable that is unknown, okay? So the way that you can start an exercise is by saying m1 times v1b, meaning the momentum for the first object b before the interaction, plus m2 times v2b, which is the momentum for the second object before the interaction. Okay, so I'm adding the two momentums before, and then they need to be equal to the momentum after. So you get m1 times v1a, which is the momentum of the first object after the interaction, plus m2 times v2a, which is the momentum of the second object after the interaction. Okay? So if you do it that way, it doesn't matter how many variables are unknown, you will be able to get an answer, okay, and the right answer. Now, in case you do not understand why the formula should be that way, I'm going to show you how you can derive the formula, okay? So the formula for conservation of momentum is there written, okay, m1 v1b plus m2 times v1 v2b, so you know the formula. And I'm saying the same way, but now instead of using b and a, I'm going to use u for velocity before and v for velocity after, which is something that you do later on in physics, okay? So I'm going to write it as this way, all right? Now, let's imagine two colliding objects, for example, the balls that I have there, okay? And I'm going to call ball A and ball B. They collide, ball A makes ball B move. So the force on the ball A due to the ball B is going to be called F1, and is force times mass times acceleration, which means that is m1 v1 minus m1 u1 divided by t. Now this comes because you know that impulse or change in momentum equals the force times the time. Therefore the force is the force will be the change of momentum over the time, and the change of momentum is the final minus the initial momentum. So I get m1 v1 final momentum minus the initial momentum m1 u1, and then all divided by t, again because force equals change of momentum or impulse over time, okay? I can do the same for ball B due to the ball A. So the force on ball B due to the ball A is going to be F2, which is as well mass times acceleration, and again change of momentum over time. So m2 v2 final momentum minus m2 u2 initial momentum divided by t, the time of the interaction. Now, if I apply Newton's third law of motion, I know that the force 1 needs to be equal in magnitude, so same number, but opposite in direction. Therefore, because forces are vectors, I put a minus. So F1 equals minus F2, okay? So I'm picking the formula for F1, and I'm substituting under F1, and I'm picking the formula of F2, and I'm substituting under F2, and I'm putting the brackets here because the minus sign applied to everything that is in there, okay? So m1 v1 minus m1 u1 divided by t, the time, equals, and now I'm applying the minus sign, okay? So it's equal to minus m2 v2 minus minus, so plus m2 u2 over time. So I swapped the positioning of the u and the v because I wanted to have a plus first and then a minus after. And this minus makes m2 v2 to be a minus, and minus and minus, minus times minus makes m2 u2 to be a plus, okay? So then I take the t's away and I get m1 v1 minus m1 u1 equals m2 u2 minus m2 v2. And I'm going to shuffle the things around again because I want all positives, okay? So I'm going to move this guy away, and I'm going to move this guy away. And that way, not only I shuffle the positives, I get all the types of velocities in the same side of the equation. So if I shuffle them away, and in this case I shuffle them away and multiplied by minus 1, I get m1 u1. So you can imagine that I multiplied here by minus 1. And then this would become minus 2 u2, so it goes here on the other side as a positive, plus m2 u2 equals, so this guy would be, if I multiply by minus 1 is negative, and I'm moving to the other side of the equation, so it goes positive, m1 v1, and then this guy, when I multiply by minus 1, minus times minus gives a positive, plus m2v2. So I just demonstrated the formula using Newton's third law and looking at the forces applied to each of the objects and considering that force equals impulse over the time, okay? Now, conservation of momentum, I have here a video just a little bit for your engagement really, about why conservation of momentum is really cool. So I'm going to put that link in the description. It's just tricks that you can do in pool or pool shots where you can use some tricks where you use conservation of momentum and also some friction and all this stuff. Of course, it's not just conservation of momentum. So you can go around and see the video, otherwise there is nothing in the lesson that you're losing, okay? Now, if two objects stick together after the collision, then that means that their final velocity will be the same. So there is something that you can do in a formula that makes it easier. So the momentum before, m1 u1 plus m2 u2, is going to be equal to the momentum after, but v1 and v2 will be the same. So I can just put it as v, okay? So if I have m1 times v plus m2 times v, I can actually get m1 plus m2 inside of the brackets, all multiplying v, okay? And this is again because both objects have the same final velocity. And this is just the way that my exercise gets simplified, okay? And again, remember that velocity is a vector, and you need to take the negative when, make it negative when you need it. So in a head-on collision, for example, okay? So here's a head-on collision for you, where you're going to see that if you would not make one of the velocities negative, you would get the exercise wrong, okay? So it says, a car of mass 600 kilograms travels at a velocity of 25 meters per second, collides, this obviously is make-up numbers, collides with a lorry of mass 2,400 kilograms, traveling at a velocity of 10 meters per second. They stick together after the impact or collision, show that their velocity immediately after is 3 meters per second. So this is what I do. First, I get the formula. And I get the formula written in full, okay? And then under each part of the formula, I'm going to substitute the values. So m1, the first mass, 600, times u1, velocity in the beginning, 25, plus m2, second mass, 2,400, times velocity. Now, collides with a car that is traveling at another velocity, but is head-on, so that means that 10 is in the opposite direction than the 25. So I would multiply by 10, negative 10. So it becomes 600 times 25 minus 2,400 times 10. All of this is equal to m1 plus m2, the two masses, times v. Because v1 and v2 are the same, they say that the velocity, they stick together after the collision. So now I just rearrange everything or carry on with the calculation. So I get 15,000 minus 24,000 equals 3,000 times v. Taking this away from that, I get minus 9,000 equals 3,000 times v. This guy needs to go and divide on the other side. So velocity equals minus 9,000 over 3,000, which gives me minus 3.0 meters per second, okay? So actually, when I say they're in the question, show that their velocity, I should say speeds, because I get a minus sign, okay? So the speed after the collision is 3. Because I have minus 3 meters per second, I'm saying that I'm going, when they stick together, they go and they carry on in the same velocity as the lorry that had 2,400 kilograms of mass, and I know that because the velocity has the same sign as the velocity that I gave to that lorry, which was minus 10. So because my final result is minus 3, it means that I'm going in the same direction as the object that had a velocity of minus 10, which is the lorry, okay? So that's an example on how you can do conservation of momentum questions. You need to practice them. There are several different types of questions with both objects stationary in the beginning or head-on collision, or one object hitting a stationary object. So give it a go, practice as much as you can, And up to then, my next lesson, which I don't know what is going to be, but you will see anyway. Up to then, be happy and healthy. If you have any questions, just let me know. Bye!